Hi, everyone. Thanks for joining us for today's guest webinar, Improving Contraflow Left Turn Lane Design and Signalized Intersections to Decrease Traffic. I'm John Patinos. I'm a project manager at the C2 Smart Center. We're a US DOT designated Tier 1 University Transportation Research Center tasked with leveraging recent advances in big data and technology to solve today's most pressing urban mobility challenges. I have the usual few quick notes to start. Questions make the webinar more interesting for you, for me, and for the presenter. So I encourage you to ask anything that you're curious about today related to the presenter's work, of course, in the Q&A at the bottom of the screen. We're going to devote 15 minutes or so at the end of the presentation to Q&A from the presenter. I think today is especially special because we're welcoming back an NYU Tandon alumni, formerly Polytechnic University. Dr. Yi Chi is the chair of the Transportation Studies Department and a professor at Texas Southern University. Dr. Chi has directed more than 20 externally funded projects sponsored by various federal and local government agencies, has more than 50 journal publications, numerous conference proceedings, technical report publications. Her research areas include transportation safety analysis, traffic signal operation, intersection geometric design, and GIS-based transportation system performance analysis. As I mentioned before, she's received both MS and PhD degrees in transportation planning and engineering from NYU Tandon, formerly Polytechnic University of New York. And we're very happy to welcome her back virtually to the campus, hopefully to welcome her back in person one day. Dr. Chi, please take it away.
Thank you, John. Thank you, John, for the introduction. Good afternoon, everyone. Can you all hear me?
Yeah.
Okay. Good afternoon, everyone. My name is Texas Southern University, and today is my great pleasure to be here to talk about one of my research on contraflow left lane design at signalized intersections. So I'm not sure if you heard about this design, but it's a very, very new design. We have not seen this in this country yet, but this design has been widely used in China and has been quite successful. So that's why I would like to introduce this new design to you to see if we can use this new idea to improve the intersection operation and the safety in our country. Okay, so this is this presentation. Before that, I just want to briefly talk about myself. As John already introduced, I'm the alumni of NYU Tandon. I graduated in 2002. So this is a picture I took 20 years ago in front of Roger Hall. Okay, you can see I look much younger and different. So after I graduated from Tandon, or called Polytech institution at that time, I joined the Texas Southern University as a faculty. I started with assistant professor, then gradually promoted to the professor, and I also served as a chairman for the Department of Transportation Studies. Okay, so my research areas. I have done research in different areas, but mainly belong to 4 areas. First is the safety and crash analysis. I remember my PhD study, my dissertation is about incident data analysis and incident delay estimation. And when I was in Texas, I started to work on several projects related to roadway geometric design and traffic signal operation and analysis. So I also have done some research related to transportation air quality analysis, such as like a vehicle emission modeling. So this is my major areas. So let's talk about this presentation. So for today's presentation, I give you a little bit background. I started work on the innovative intersection design since 2012. At that time, I'm working on a research project for TechStart. This is to evaluate the implementation of several innovative intersection design that has been implemented in Texas. So I did the research on continuous flow left turn design and on Michigan U-turn and the super straight design. Okay, so since that time, I was really interested in this kind of topic because I think we can use better design to improve the intersection operation and improve the safety. So back to 2018, when I traveled in China, I saw a very interesting design. In China, they call the borrowed left-hand lane design. But in here, I saw some literature, they all call it contraflow left-hand lane design. So I started to work on this new design, and I studied its benefits, the safety concern, and particularly how to design the signal timing and how to design the geometric layout for this type of intersection. And I also investigated how to implement this design at an intersection with split phasing. So this is a very special signal phasing. And I have some interesting findings, so I would like to share with you today. Okay, so let's talk about what is this contraflow left-hand lane design? So here is a graph, a figure to show you the geometric layout of this new design. So in this graph, you can see at this intersection, we have 4 lines. I marked them in the green color. This is called a contraflow left-hand lane. So basically, this 4 lane was on the opposing through traffic lane. Okay, so the basic idea for this design is at an intersection, if you have very high left-hand traffic, but you don't have space to build an additional left-hand lane. So what you do is you use the opposing through lane as a temporary left-hand lane to move your left-hand traffic. So in this way, you can increase your left-hand capacity. Okay, so how this will work? So the idea is like you put signal lights in the median opening. So this is the entrance of the contraflow left-hand lane. So this signal lights is called a pre-signal light. So by coordinate the pre-signal lights with the signal lights at the main intersection, you can control the traffic that when they can enter the contraflow left-hand lane, when they can't. Then you can avoid the conflicts between the left-hand vehicle and the opposing traffic. So in this way, you can use this lane as additional left-hand lane. So this is a basic idea. So here is the definition I put on the paper. It provides additional left-hand lane capacity by making use of the opposing lanes dynamically through appropriate traffic signal control. So this is the basic, design concept. Okay, so this design has been first implemented in 2014 in China, and then it has been, widely implemented in more cities. Back to 2018, it has been more than 20 cities use this design, and the results is quite good. They all report this design help reduce the congestion at the intersection, and then make the intersection, operation more efficiently. So this is a design idea. So I use this simulation to show you how this works. So in this simulation, I highlight this lane. This is the contraflow left lane. Okay, so you see before the lane we have a pre-signal lights. This bar indicates the pre-signal lights. So let's see the simulation. Yeah. So you see now this lane was used by opposing through traffic. So opposing through traffic, the pre-signal is red. No left-hand vehicle can enter the contraflow left-hand lane. So after that, we cut the signal, then we let the opposing crossing stream move. So now it will turn green, so the vehicle can enter the contraflow left lane. So this is the phase we move the cross. Now the main intersection left hand phase signal turn green. Then all the vehicle on this contraflow left lane can be discharged from intersection. So we can clean the vehicle on the contraflow left lane. So after that, we cut the signal, we release the opposing through traffic. Then the opposing through traffic can use this lane again. Okay, so this is the whole idea. So how we make this work. Okay, then I will show you another video. This video shows this real world intersection that using this design. So you can see in this graph, there's a signal lights in the middle of the streets. So this is the pre-signal lights. So there are some vehicle lined up in front of these lines, this vehicle try to enter the control flow left turn lane. So let's see how this works in the real world. So you can see now it's the signal still red. The opposing traffic was using these lanes. Now the signal turned green, those vehicle moved into this opposing lane. Okay, after that, the main intersection, left turn face turn green. So all this vehicle from the control flow left turn lane can be discharged from the opposing lane. Okay, after that, they cut the left turn signal, they release the opposing through traffic. Okay, so now the pre-signal lights is red. No left turn vehicle can enter it. Okay, so this way they avoid the conflicts between the left turn and the opposing through traffic. Okay, so why are interested in this particular design? First, as I mentioned, it will increase left turn capacity because you tripled and you doubled and tripled the left turn lane. So this is a big benefit. I like the idea, like it's using the existing facility. You don't need to build any new lane, but you kind of increase their capacity. The second is it's quite easy to implement. So you can see in this video, they just put a signal lights in the median and then draw something on the pavement mark to indicate this control flow left lane. Then it can be used. So I think it's very easy because I have been working on other innovative intersection design like continuous flow left turn design. All this innovative design, they require to build a particular channel to move the left turn vehicle. They require to put some barrier in the median to prevent a certain movement. So all this new design always involved in some major modification of the intersection that needed to do lots of construction work. But this design is quite easy to implement. You don't need to do lots of construction work. So this is a major benefit. And another benefit I want to mention is for all this kind of new design, we engineers think it's a great idea. It will work very well. But when you implement it in the real world, sometimes it may work very well to reduce the delay and make the intersection operate better. But you also complain from drivers. So the driver will get confused by all this new design. So sometimes you have to take it back because of the complaints you received from the driver. So this happened in Texas. Back to 2010, which implement the Michigan U design in Plano, Texas. Everything works well, and even the incident rate is not increased at all. But we got so many complaints from the roadway user. So later, back to 2014, we have to take it down. We have to convert it back to the regular intersection. So for this kind of new design, this thing will happen. So if we use control flow left-hand design, it's very easy to take it back. You just take off the pre-signal lights and erase the pavement mark. You can easily, take it down. So this is the benefits of using this new design. But there's some safety concern for this design. First, you allow the vehicle use opposing lane. That's very dangerous. Because how about the left-hand vehicle cannot be cleared from the intersection before the signal turn red. So they will be trapped on this left lane, and then we'll have hands-on collision with the through traffic. So that's a very dangerous situation. And so that's the major concern for using this type of design. Another thing is the designers are opposing through traffic. The vehicle on this control left lane also will conflict with the turning traffic from the crossing street. Both right turn and left turn will potentially turning to this control flow left lane to have a collision with the vehicle on the control flow left lane. Okay, so these are the safety concerns. So I think because of this safety concern, people have not been used this design in this country yet. But I think we can, using the signal timing design, we can carefully get the signal timing and the geometric layout for this type of intersection to prevent such accident, to prevent the risk associated with this design. So let's talk about how we make the signal timing and the geometric design works for this type of design. First is the signal timing. So here I draw a signal timing diagram to indicate the signal timing strategy for this type of intersection. So in this signal timing diagram, in the middle, the solid arrow indicates the signal phase at the main intersection. Okay, this is the main light. And then in this both sides, I put some horizontal arrow. That is indicated the signal phase at the pre-signal lights. For example, this 1' is a signal phase control the westbound left-turn vehicle that will enter the control flow left lane at the pre-signal light. Okay, so let's use this direction as an example. So you can see the pre-signal light turned on during the time when we move across the street, cross street through movement, like phase 8 and phase 4. This is the south and westbound cross street through movement. So we turn on this pre-signal lights at this point. So the vehicle can enter the control flow left lane to wait at the control flow left lane. Then the signal at the main intersection, the left signal, it means the phase 1 will turn green. Then the vehicle can be discharged from the intersection. Okay. After that, we'll cut the signal lights at the pre-signal lights first. So the pre-signal lights will be cut first. Okay, then no vehicle can enter the control flow left lane. After that, we also will cut the signal at the main intersection. The left signal will turn red. Okay, so the time between these two signals turn red is the clearance time. This time we use to clear all the vehicle on this control flow left lane. So the key thing is you have to make sure we provide enough time to clear all these vehicles. So this is a very important clearance time. We call it end clearance time because this happened at the end of the pre-signal phase. So here is the way we estimate this pre-signal end clearance time. Okay, so basically this clearance time was determined according to how many vehicles will be on the control flow left lane. So this also depends on how long this control flow left lane will be. So this equation we use to estimate it. So basically we estimate the number of vehicles, use the length of the control flow left lane divided by the average storage length for the vehicle. This we calculate the number of vehicles, and we multiply by the saturation discharge headway. Okay, so the time we use to discharge each vehicle. Then we plus some startup loss time. So this is the total time we use to clean the vehicle. So we call it the end clearance time. Then besides this end clearance time, we also will make sure the signal lights. We will clean all the vehicle on the control flow left lane. So this is the left turn from the cross street, because before we turn on these lights, we will cut the left-hand vehicle from the side street first. So for the left-hand vehicle, they have some all-red time, but this all-red time only can clean the vehicle from the intersection, not from the whole, control flow left-hand lane. So we needed to add this clearance time. So this time was calculated according to the length of the control flow left-hand lane divided by the speed of the vehicle. So we use the 15% of approaching speed to make it more safe. Okay, so this we call the pre-clearance time. That means we have to start the signal a little bit late, wait until all this vehicle clear, and then we turn the signal on. Okay, so we have both clearance time. One is before the pre-signal phase, one is the end of the pre-signal phase. So here are the two clearance time. Okay, so this is the signal timing design for this type of intersection. You can see the signal will work with this lead left-hand phase. So we always let left-hand move first. Okay, the reason why we only can use lead phase is, let me show you. So we have different phase sequence: lead, lag, and lag. So this only can work with lead, not work lag, not work with lead lag. The reason is if you have any lag phase, before the lag phase is opposing through phase, right? So the opposing through vehicle needed to use this control flow left lane. So you are not able to let the vehicle enter the control flow left lane to wait for the signal turn green. So in this way, the control flow left lane design cannot work because the control flow left lane have to be available before the left turn phase. Okay. So this is the signal timing requirements. Okay. Then let's talk about geometric design requirements. How we make things work. First, if you have multiple left-hand lane, you need to make sure the cross street have enough lane to receive all this left-hand traffic. So there should be enough receiving lane for the cross street. Another thing is the right-hand traffic. As we mentioned before, the right-hand from the cross street also will conflict with the vehicle on the control flow left lane. So for this kind of design, we strongly recommend to use channelized right-hand. Or we can put like some pavement mark to clearly indicate the right-hand phase, the right-hand path, to avoid the right-hand vehicle turning on the control flow left lane. Okay, so this is the right-hand channel. And another thing is how many control flow left lane we can use. If you notice in the video I show you the real world video, they use both lanes as a control flow left lane. Yes, technically you can use all the opposing lane, but for us, we not recommended you to use more than one control flow left lane. And the reason is if you have used two control flow left lane for each direction, that means you have triple left-hand lane for each direction. And this design only work with lead phase. So that means all these left-hand have to move together. Okay, all these three, triple left-hand lane, it's not very safe to allow this kind of operation because very likely you will have very small space between the turning paths from both directions. So you have insufficient, separation for the turning paths. That was not safe. Okay, so this is the number for control flow left lane. Okay, another thing is about U-turn. For this kind of intersection, U-turn should be prohibited. The reason is first, you cannot let the people make U-turn from the regular left-hand lane because they have the control flow left-hand vehicle on their left side. So if they make U-turn, they will have conflicts. Then for the vehicle on the control flow left-hand lane, it's also very difficult to make U-turn because you are in the opposing lane already. So there's no median to separate the turning lane and the receiving lane. So there's no enough space for people to make a real U-turn. So for example, if you want to let people make a U-turn, you have at least like 36 feet separation. That means you need to have at least the 3 lanes between the control flow left-hand lane and the receiving lane. And also we need to have a particular lane for receive the right-hand lane. So that means you need to have at least 6 lanes in one direction. That's not very likely for a local intersection. So that's why the U-turn should be prohibited for this type of design. Okay, another very important thing we need to solve is where we should put the pre-signal lights. That's a very important design element. Or how long the control flow left lane should be. Okay, so for this question, first the control flow left lane could not be very short. If it's very short, that means only few vehicles can enter the lane if the signal turn green. So that means we are not fully use the control flow left lane. The benefit is very low. If you have the control flow left lane very long, that means you have to put the pre-signal in a very far place from the main intersection. The problem is the pre-signal lights only turn in a very short time period. Most of the time when vehicle arrives, they will see the pre-signal lights is red. So all these left-hand vehicles have to line up in the regular left-hand lane. Then they will miss the opportunity to enter the control flow left-hand lane, because when the pre-signal lights turn green, they're already on the regular left-hand lane. So there's only few vehicles can enter the control flow left-hand lane. Okay, so in this way, the utilization rate is still very low. Okay, so the ideal situation is the control flow left-hand lane length should allow the left-hand queue evenly distributed on the regular left-hand lane and the control flow left-hand lane. So that's why the length of this control flow left-hand lane should equal to the queue length. You can estimate the queue length, or you can observe from field how long the left-hand queue length will be, divided by the number of left-hand lane, including both the control flow left-hand lane and the regular left-hand lane. So in this way, the queue length will be evenly split on a different left-hand lane, that to ensure the utilization rate of the control flow left-hand lane reach the maximum level. Okay, so this is the how long the control flow left-hand lane should be. So this is an important design concept. And in order to design this kind of intersection, we have to determine the signal timing and the length. These are two major things we have to determine. So, and these two things have some interactive dependency between them. So the signal timing at the main intersection will determine the left-hand queue length, and the left-hand queue length will determine the how long the control flow left-hand lane should be, and then all these things will work together to determine how the pre-signal timing should be. Then the pre-signal timing also will affect the utilization rate of the control flow left-hand lane. So finally, it will also affect the main intersection design. So there's a loop, a feedback loop between these two elements. So I proposed a method to determine them in one procedure. So this method was you can find this method in my paper recently published. So this is a paper, open access paper. You can type it in a Google Scholar. You can download it. So in this paper, I proposed this procedure. There's a 4-step procedure to determine both signal timing and the control flow left-hand lane length at one like try and error and iterated procedure. Okay, so this is the method I proposed in that paper. If you're interested, you can take a look at it. Then I would like to, I will not go to detail for this method, but I wanted to show you the results of the method, how we use a case study to validate this method works. So in this case study, we redesigned the signal timing and the control flow left-hand lane length for existing intersections that use this design. Okay, so here this is the existing intersection in China. So they use the control flow left-hand lane already, but the single, so this traffic condition, it's quite congested and have heavy left-hand traffic. And it's also very complicated situations. They have both bus, pedestrian, bicycles. Okay, so we go to this intersection, collect all the data. And this is the signal timing, the existing signal timing. So you can see they use lead left and face for the intersection. And so the signal timing, the problem we found is in the existing signal timing, they do not consider the clearance time. For example, the clearance time between this cross street left turn and the pre-signal lights here only 3 seconds. Okay, so that was not sufficient. The vehicle in these 3 seconds can only be cleared from the intersection, but not cleared from the control flow left turn lane. Okay, so this is the existing signal timing. Then we redesign the signal timing according to the method we proposed in that paper. And we use the traffic simulation to do the experiment to see if our new design on the method we proposed can improve the operation of this intersection. Okay, so in order to do the traffic simulation, so we use the vision traffic simulation. We did some, calibration, the model calibration. We collected the travel time data in the field. So, and then we compare the travel time data with the simulated travel time data, and make sure the things matched. That means our simulation can reflect what happened in the real world. Okay, then we redesign the signal timing according to the method that we proposed. We consider both, and the clearance time and the pre-clearance time for this pre-signal phase. And we also, determine the optimal location to put the pre-signal lights, or the optimal, length for the CLL lane. Okay, so the blue color is the existing length, what happened in the field right now, and the green color is the length we estimate according to our method. So you can see for this 4 direction, most cases they are quite close, but one exception is the sourcebound. The sourcebound, according to our method, we find that the optimal length for the CLL lane is 325, but the existing is 197 feet. So we needed to do some comparison for this case. Okay, so first we compared the overall, travel time, delay, and the average queue length at this intersection. We compared the existing condition, use existing, CLL length and existing signal timing strategy. Compared with the one we redesigned, we used our proposed signal timing and the proposed, CLL length. So we compared the results. We found that by using our method, we can reduce the travel time, reduce the delay, and also reduce the queue length at this location. So that means our method works better. Then we also test if the control flow left hand length we estimate for the sourcebound is the best length. So the location we recommend is 325. So we gradually change the length from 225 to 425. So we increased gradually. So here the results show the intersection travel time, delay, and the queue length for all the traffic. This is only for the left turn traffic. Okay, so from this graph you can see the points, the 325 feet, the location is the best location. So if it's shorter than this location, the delay is high and the delay was decreased until to this location it's become lowest point. Then if it's become longer, it will increase again. So that means the location we recommend is the best location for that approach. Okay, so here's the finding from this case study. So what we found after we redid an intersection, signal timing, and the CLL length, use the method we proposed, the average travel delay and the travel time and the queue length was reduced. So this is very good results. Another thing we want to see is the signal timing we propose. We consider both, clearance time, both pre-clearance time and the clearance time. And in this way, we can avoid the risks that are associated with the use of the CLLs. So we make things work more safer than the existing signal timing. So this is the two findings we got from this study. And then the next thing we did is we wanted to know if this design can be used at a signalized intersection that using the split phasing. So why we have this question? First, let me introduce what is split phasing. The split phasing is a very special, signal phasing. So in this design, we give the signal the green lights to one direction first. Okay, we allow the left turn and the through movement from one direction move at the same time. Then we switch the signal to another direction. Okay, so the reason we use this split phasing is because in some location we have high left turn demand, but we don't have space for our exclusive left turn lane. So in this way, we need to use split phasing because we don't need to have a particular lane for. We need to have build a left turn lane. We can let the left turn and the through move together. Because they move together, so they will not block each other. So that's the only way we don't need our exclusive left turn lane. Okay, so this is the case we need to use split phasing. And another thing is the split phasing also have some benefits in and certain traffic conditions. For example, if the traffic from one approach is balanced, that means the different movement like the left turn and the through from one direction is very close. So, for example, the left vehicle pylon is very close to the through vehicle pylon for one direction. But meanwhile, the traffic from the opposing direction is not balanced. Like one direction is heavy, one direction is very light traffic. So in this kind of situation, use split phasing will have more operational benefits. Okay, so this has been approved by a previous study. So the thing is, you can see because the Contraflow left turn lane design have the same purposes. They also wanted to move more left turn traffic, but do not want to build additional left turn lane. So the question is, can we use this design at the intersection that split phasing is needed or is recommended? But the problem is, as I mentioned before, the Contraflow left turn design only works with the lead phase. So it cannot work with any lag phase. But in the split phasing, you have one direction has to be the lag phase, right? Because you switch the signal between the direction. So one direction has to be lag. So in this way, we cannot directly apply the CLL design at the intersection that using the split phasing. So how to solve this problem? In order to address this problem, we proposed a new signal timing strategy called counterclockwise split phasing signal timing. Okay, so we call it the CSP signal timing. So how this works? So the whole idea is we assign the signal in this counterclockwise direction. For example, first we let the north traffic move. When we give the green lights to the northbound traffic, to the southbound traffic, we let the westbound pre-signal lights turn green. Okay, so in this way, the westbound left turn can enter the Contraflow left turn lane. After that, we switch the green lights to the westbound. Then all the vehicle enter the Contraflow left turn lane can be cleared from the westbound. And the same thing, later we switch to the southbound. And after that, we can switch the green lights to the eastbound. In this way, the Contraflow left turn lane design can work with this split phasing. Okay, so here is a traffic simulation show you this design idea. You can see it first, this bound moving. After that, this bound. So you can see they are working in the turn in this kind of counterclockwise direction. Okay, so this is the vision traffic simulation for this type of signal timing design. Okay, so we also develop a particular procedure to design the CSP signal timing for a particular intersection. So this is the name of the paper. You can also find it from the Google Scholar. Okay, so in this study, we also did a case study. Okay, we wanted to approve our concept to see what's the benefit to use this CSP signal timing design. So we used a hypothetic intersection to show the results. Okay, so this is a hypothetic intersection. The reason we use hypothetic intersection, we want to make sure the traffic condition is ideally for using the split phasing. So you can see in this intersection, we have the traffic volume in one direction is quite balanced. You can see the left-hand vehicle per lane and the through vehicle per lane is the same. And but for the both opposing direction, the traffic is level is different. Like this southbound have more heavy traffic than northbound, and the westbound have more traffic than the eastbound. So this will be a perfect traffic condition to use the split phasing. So here is the single timing, the split single timing we designed according to the traffic volume from all the approach. Okay, so this is like a baseline model, the base condition without CLL lane. Okay, then we try to implement this CLL design at this intersection. So we add the CLL lane, and then the traffic condition is the same, but we redesign the single timing. First, we use the CSP signal timing strategy we proposed before. The second, we just use the current signal timing strategies people used for the CLL lane design. This is use the lead left-hand phase. Okay, so we do this both signal timing, then we did the self-traffic simulation to compare the results. So we designed 3 different scenarios, different type of scenarios. The first one is we try to increase the whole intersection volume from low to high to see what the results will be. The second one is we only increase the left-hand traffic because we know the CLL lane design is mainly for address the heavy left-hand traffic volume problem. Then the third one is we try to see if we make the traffic condition even more unbalanced. Okay, what will happen? So this is the 3 type of different scenarios we tested in the simulation. So this is the first one. The first results is we increase the traffic volume from the 100% to 140% for the whole intersection. So you can see in this graph there are 3 lines. The light color line is the base model, the model without CLL design, only use the split phasing at this intersection. This dashed line is a design. We use CLL line design, but we use the existing lead left-hand phase. Okay, the solid dark line is a line for the intersection with CLL design and using the CSP signal timing we propose, the counterclockwise signal phasing. So you can see from this graph, the signal timing, the CSP signal timing works better than the existing lead signal timing for this intersection for all the traffic volume conditions, and also they works better for the base condition, like without CLL design. So this just tells us the CLL design can help increase can help improve the operation of the intersection, and our CSP signal timing works better than the existing signal timing strategy. Then we also tried the left-hand volume condition. We increased the only left-hand volume from the 100% to 150% at this location, and you can see this result show you like with the left-hand volume increased, these 2 lines, the dashed line and the dark line, have more difference with this light line, with this base condition. So that means this, because these 2 lines is for the situation with the CLL design, the control left-hand design. That means if you have heavy left-hand traffic volume, if your left-hand traffic volume become more and more heavy, use the CLL design will give you more benefit. Okay, so let's show the advantage of use CLL design, the control left-hand design. Then let's make the traffic condition even more unbalanced. So as I've talked about, the westbound have more traffic than the eastbound. So now we gradually increase the westbound traffic from 100% to 160% to make the situation even more unbalanced. So in this results, you can see our CSP design have more benefit than the existing lead left-hand design for the CLL lane design. So this is because our CSP design we still use a split phasing. Okay, because the lead is not split phasing. So our CSP design allow us to use both CL design and the split phasing. So that's why when the traffic condition become more unbalanced, our performance become bad. Okay, so the reason is this CSP design allow you to combine the benefits of the control left-hand design and the split phasing design. Okay, so this is the major findings. Okay, use the proposed CSP single timing can combine the advantages of split phasing and the CLL design. Therefore, it achieves more operational benefits at the intersections where the split phasing is required or recommended. Okay, so this is our major finding for the second the study. So here's the overall conclusion and the recommendation we can got from both study. First, the CLL design can reduce the traffic congestion at the intersection, especially as the intersection have heavy left-hand traffic. Second, we should very carefully design its signal timing and its geometric design. All these design elements have been carefully, considered when we implement this new design. Okay, especially the signal timing things. We have to make sure we have enough clearance time to separate this conflict traffic flow to avoid the risk associated with this type of design. The third one, I want to just emphasize we propose this CSP signal timing strategy is a good solution for using the CLL design at the intersection where we need to use the split phasing. The third one, the last one, for this kind of new innovative design, we always need to provide enough pavement marks, traffic signs. We have to put lots of advanced traffic signs, let people know what the design is, how they can safely go through the intersection. So this is always very important for using the innovative intersection design. Okay, so that's the things I want to present today. Now I open to your questions. So any questions?
Professor Shi, thank you very much for this very interesting presentation. I have a couple of questions, and it seems like there's one or two questions from the audience.
Okay,
so I'm gonna open with mine, and then we'll get to Adrian's right after that.
Sure.
So I was wondering if there are, you talked about safety concerns and you presented some simulation results, and you also mentioned that there was actual implementation of this technology in Texas. I was wondering if there were any problems from the behavioral perspective safely introducing this technology when frequent drivers may be accustomed to existing traffic infrastructure, and then all of a sudden, on your ride home, you have this introduced change to the infrastructure. How that is addressed, or how it was addressed in Texas?
Okay, very good question. Yes, that's a very important issue. When we implement this new design, as I mentioned, we always needed to consider what the driver will feel. Okay, are they comfortable to use this new design? All of a sudden, the things changed for them. And actually, this thing had not been implemented in Texas yet. It has been implemented in China widely. They have like more than 21 cities use this design. So I read a paper, particularly for the safety, since they did a safety study at these intersections. They collect the real world data, real world accident data. Yes, there's do have some accident happen in this kind of intersection, but it's not a very severe accident, okay, and not cause bigger safety problem, and it maybe have some disturbance in the traffic, like people stuck in the country for left lane, they have to back to exit to the country for left lane to give to yield to the opposing traffic. So there's a study. Talk about this safety problem and the Java behavior problem. I can send you these papers later. Okay, so if you're interested, you can take a look at it.
Sure, that sounds great. Okay, so question from Adrian. And by the way, I didn't mention this at the beginning. You can, of course, ask your questions via the Q&A function at the bottom of the screen. And you can also, if you'd like, raise your hand and I will try to unmute you and you can ask your question directly to Professor Chi. So this question from Adrian. Hopefully I get this right. In the real world video that you showed, a couple of the vehicles in the opposing direction had not passed the pre-signal point before it turned green for the contraflow turns, but those opposing through vehicles weren't in the contraflow lane, so everything still worked as designed. Is there a lane-specific signal, like an X above the through lane that tells through vehicles not to use the left through lane when the opposing pre-signal phase is green? Did you get that? There's a lot there.
Okay, so can I go back to that video because then I can more clearly know?
Yeah, definitely. Go for it. Yeah.
Let me go. Okay, I think that's some good observations. Okay, let me.
Yeah, definitely go to the video and then Adrian, you can feel free to write in to clarify or to ask your question directly.
Okay, so this is a video. Okay, at the beginning you see that this opposing traffic is moving. Okay, so let's see what the observation is. Okay, now it's turned green, right? So they moved into the counter for left lane. Okay. This is a right-hand vehicle at that time. As I mentioned, right-hand, they can turn it on red. Okay, so these are all red-turn vehicle, right? This is a vehicle turning from the cross street, not opposing.
Yeah, so is there a lane-specific signal? Okay, so Adrian writes, as it turned green, there were two vehicles still traveling in the opposite direction, though it's possibly a video lag.
I think it's a red-turn vehicle from the cross street. So all these vehicles from red-turn, the opposing vehicle should not move, because when you have the green lights for the left turn, all this opposing should stop. They could not move. See, all this is from right turn. Now the opposing start move because you already cut the green lights, right?
Yeah.
Okay. Yeah. So basically, you can see from this video the conflicts between the right turn and the country for left turn vehicle is very possible. So that's why I recommend the channelized right turn. If you want to make sure things work, safely, it's better to have a right-hand channel instead of let the right-hand can choose which lane they can move in. Right.
So I have another question here from Kingsley. Exclusive left turns, like left turn only, is typically used when you have more than 200 VPH. Is this method used where it is exceedingly higher?
That's true. Yeah. You can see from the case study I gave you the left turn volume is very heavy at certain intersection, like they exceed the capacity if you only give one left turn lane. So that's why they try to use adding another left turn lane. So that's the whole purpose for this design.
Okay, thank you. So I apologize if I misheard you earlier, but you said that it was implemented in Texas or it was not?
It was not.
Okay.
Yeah, in Texas, we implement like continue flow left turn lane, this kind of design, but not country flow left turn lane. No, not yet.
Gotcha. Okay. Okay. You were talking. Okay, I see. You were referencing complaints about implementation of that turn lane style.
Yes, yeah.
Okay. Are you familiar with any, or probably there's several, like post-implementation evaluation to look at the benefits, travel time, and congestion reduction for drivers in places where this has been implemented? Like, what kinds of impacts are we talking about?
Yes, yes. For me, I personally did this study for tech study for other innovative design, like I mentioned, the continuous floor left lane, the super straight design. I did the post evaluation. Most of the innovative intersection, they works very well. They reduce the congestion, they reduce the delay, they also reduce accident rates. But the big issue we find is driver acceptance.
Yeah.
As you mentioned, some drivers don't like it.
Sure.
So that's the big issue we find when we implement this innovative design. So the campaign is very important. So right now, I think before you implement it, you have to let driver know. You have to put it in the YouTube video, put it in the social media. It's better to have people develop some flyer and go to the intersection to distribute to the people who frequently use this road. Let them be ready what will happen before you implement this new design.
Yeah, so I guess relatedly, we of course are a research center with many transportation engineering doctoral students. For students who are interested in this type of research, you mentioned one large one, which is behavioral design. What are some problems that students should really focus their research energies if they want to advance this technology?
Very, very good question. Okay, yes, I think we need to think about how to, because we cannot only depend on traditional way like signal timing geometry. Even I talk about this a lot into this presentation, but in order to prevent all this human being error, human effect, we use technology is a better way. Let's think about how we use the sensors, the detectors to make sure all this vehicle in this country for left will be clean before we allow the conflict traffic can release conflict traffic. So I think we can think about how we can use technology to make sure 100% safe to use this kind of a new design.
Okay, great. Question from Kingsley about enforcement. How is enforcement of this particular, I guess, compliance with these turn lane technologies enforced? Maybe the same way that any other are enforced.
Okay, yeah. For this type of design, as I mentioned, I can send some paper to talk about the enforcement and the safety thing. But I can talk about the other new design has been implemented in Texas. Okay, so the enforcement here, the tricky thing. Like at the first half year, this is a learning curve. When this thing implemented in the first half year, the enforcement is very important. So the policemen have to be there to make sure people follow the rule. And one of my the presentation I give, I show you the ticket the police officer gave during the period. Like the first half year, they issued lots of tickets. Then later, after the half year, the thing was kind of reduced, become okay. So yeah, the enforcement is a very important issue, especially the first half year.
And I'm sure that those enforcement issues generated some of the complaints that that cause certain types of traffic technologies to be rolled back. Final question, my favorite question: what are you working on right now, and why are you excited about it?
You currently?
Yeah, currently. Continuation of this research or anything else?
That's true. Currently, I'm working on the safety evaluation, how we can accommodate like the bicycle and accommodate the pedestrian safely for this kind of new design. And because right now in Houston, in Texas, we have so many bike lanes newly added. So if we add this new design, how we can consider all these roadway users, make sure everyone can pass through the intersection safely. So that's my current research topic now.
Yeah, absolutely. I didn't even think to ask you about bike lanes. That presents a whole other research inquiry. Dr. Chi, I just want to say thank you so much for being with us today. It's very exciting to have an alumni come back and speak to us and to our students. And I hope that we're able to welcome you in person in the coming months or over the next year.
Thank you.
Thank you everyone for your questions. Take care.
Thank you.